Here's another example. In this study, they did a seismic survey in 1990. They repeated the survey in 2000. Now we can start to see fluid movement and understand how fluid is moving through the reservoir. These surveys were done in 1985 and again in 1999, 14 years later. After 14 years, it is possible to get a picture of what is happening inside the reservoir. The effect of pressure and saturation can be identified, as well as a rise in the OWC, the oil-water contact line. Here, instead of oil, you see mostly water. Now the question is to determine if it will pay to continue drilling or to shut down this field. The advantage of 4D is that of the four variables of rock properties, density, elasticity, porosity, and fluid saturation, only fluid saturation can be tracked over time. 4D seismic allows the geoscientists to see these changes over time. These examples, I think, make it clear how useful 4D seismic surveys are in understanding the effects of the changes that take place over the life of an oil well and its reservoir. Mature, producing reservoirs need frequent monitoring to help identify drilling options, select well intervention opportunities, locate untapped reservoirs, and monitor field development. To construct seismic surveys like the following. In this survey, you can see physical properties or shapes of a formation. They have been colored by our geoscientists to allow us to see more easily the shapes or formations. In essence, these surveys allow us to see what is in the subsurface. Remember that geology is a spatial science. Its primary mandate is to define what type of rock occupies what space. They can then construct fairly accurate pictures, maps, and models of what is in the subsurface. In the second phase, data processing, it is all about collecting the data and compiling it so that it later can be read in the final or third phase of data interpretation. Here is an example of a seismic chart where each line represents a wavelet and a geo or hydrophone receiver. You might have 40 or 50 in your array. Recording of a wave reflecting back to a receiver. Now, if you remember, when we first started talking about waves, I mentioned that the highest point of a wave is called a peak. It is given a plus value. The lowest point of a wave is called the trough. It is given a minus value. Let me show you how the geoscientists use the plus component of a peak and the minus component of a trough. I think this can be illustrated more clearly if we rotate our image of a wave 90 degrees so that it looks like this. The horizontal angle of the peak is just a little higher and to the right of the trough, which is a little lower and to the left. If we color the peaks black but make the troughs white, we can start to see patterns. These patterns take the form or mimic the pattern of the rock formations below. Here is another example. Here we show 4 steps, but surveys can have as many as 25 steps or more. Remember, when I told you that in data acquisition, they send the data to large computer centers. To process this data, very large computers are necessary. Anyway, in each step, the image is made clearer. By the 4th image, we can start to see lines and shadows that resemble the subsurface geology. Once we determine the velocities of the waves, as I showed you earlier, we can determine the depths of the water. On our chart, we see that the first wave's travel time was 1 second. The second wave's travel time was 1.33 seconds. The third 1.66 seconds, and the fourth was 2 seconds. With the exact time, we can calculate the depth. Remember, the velocity of the wave changes as it travels through the different rock types. In denser rock, the waves travel faster. Using v for velocity, dz for depth of the zone, and z for the total depth, we can solve the following equation. Depth equals velocity times time divided by 2. V equals 1,500 meters per second. dz equals 1.0 seconds times 1,500 divided by 2 equals 750 meters. Z equals 750 meters. Second zone, V equals 2,000 meters per second. dz equals 0.33 seconds times 2,000 divided by 2 equals 330 meters. Z equals 1,080 meters. Third zone, V equals 2,500 meters per second. dz equals 0.33 seconds times 2,500 divided by 2 equals 412.5 meters. Z equals 1,492 meters. Fourth zone, V equals 3,000 meters per second. dz equals 0.33 seconds times 3,000 divided by 2 equals 495 meters. And Z equals 1,987 meters. So we get a total basement depth of 1,987 meters. Now, you've seen how they can use the wavelets to determine the velocity as a function of depth. They measure the time from the first wave to the last wave and then use that to calculate the depths of all these different layers or geological boundaries. As planned, they are another step closer to being able to decide where to drill the first wildcat well. Before I continue, I should explain that within the second phase of data processing, there are two methods used. Each is used for a specific purpose. The first method uses the raw data directly from the recorder with no filters, like when they measured the depth of the water in the example we just discussed. No filters were used. They just measure the travel time of the wave from the gun to the hydrophone. The second method, however, uses data that has undergone filtering. What do I mean by this? The motor noises by our own or other boats nearby, for example, create their own sound waves that could be read by our instruments. Because these sound waves may distort or interfere with our data, this noise needs to be filtered out. These interfering background noises can cause shadows or give false depths. Here is an example of filtering. Normal move out, or NMO, is a depth correction process. As you move out to the farthest hydrophones, the measured rays get longer, but the depth does not change. At first glance, it might appear that these longer reflected rays suggest increasing depths because they are longer. As we can see, however, in this illustration, the depth of the water has not changed, just the length of the reflected wave. In this case, we must make a data correction. Here is an example of a graph with the corrected wavelet using the NMO technique. By using these various techniques, the computer can adjust the data so that more realistic forms of the structures below can start to be seen. Powerful computers are necessary for these kinds of data processing.